This chapter deals with demographic change in models of endogenous economic growth, and it is built on the paper Population Aging and Endogenous Economic Growth, published in the Journal of Population Economics, and the paper Demographic Change and R&D-based Economic Growth, published in Economica and written together with Timo Trimborn. The point of departure in this chapter is the endogenous and semi-endogenous growth literature that, as we've discussed in these chapters, describes the driving forces of technological progress and therefore of long-run economic growth, depending on market forces, incentives to carry out research and development, the number of scientists in the economy, and eventually the population size or population growth. So you can see the corresponding lectures on the Roma model of endogenous economic growth and on the Jones model of semi-endogenous economic growth. As we discussed there, these frameworks are built on the assumption that a single representative agent that lives forever makes all the relevant economic decisions on the household side of the economy. And as I also said previously in the chapter on what economic models are, this assumption may be perfectly fine in the context of many research questions. It makes life a lot easier, and if we are not interested in analyzing inequality related questions or the questions related to changing demography, these assumptions may be very well justified. However, if we want to analyze the effects of demographic change, particularly changing life expectancy and so on, this assumption of a single representative individual that lives forever is meaningless. So we cannot change life expectancy in such a setting, and we need to replace this assumption by something else. Now, what we replace it with here is that we assume that each person has a certain mortality rate mu, with which it dies at each moment in time, and it has a fertility rate beta, with which it gives birth to children. And in this context, then, the population growth rate is the difference between the birth rate and the rate of death, the mortality rate mu. And then in such a setting, demographic change can be analyzed by varying these two parameters, beta and mu. If we increase mu, the mortality rate, then life expectancy would decrease, for example. So we could analyze a situation where mortality is higher, where the health of the population is lower, and ask ourselves how this may affect economic growth. Or we can vary the birth rate for a constant death rate, and this would change the population growth rate, so we can analyze independently of the mortality rate what happens if the fertility rate in the economy changes. Now, in such a setting, there are two channels by which demography can affect economic growth. One is the demand side channel, so that's how demographic change affects the demographic structure of the households in the economy and how this affects their decisions. And when their decisions are changed, this can have repercussions on the incentives to carry out research and development and then on economic growth. And the supply side channel, where demographic change, of course, has an effect on workforce growth and the market size, and thus also on the incentives and the resources to perform research and development. So the number of scientists, of course, is determined to a large extent by the size of the population and by the growth rate of the population in such a framework, and this will also be affected by demographic change. The main change on the household side is that there is not anymore a single representative individual that maximizes utility over the life cycle, but there are different cohorts born at different points in time. And depending on the date of birth, these cohorts have a different age. And with their different age, they have had more time or less time to accumulate assets. So they will be richer, some of them, and some of them will be poorer. And that will determine differences in their behavior. So we have here a person born at time t0. And such a person maximizes life cycle utility generated by consumption according to a concave utility function that we assume now is logarithmic. And the discount factor is now not only the discount rate, that is the rate of pure time preference rho, but it is augmented by the mortality rate mu, because a person who faces a risk of death is less likely to postpone consumption into the future as compared to an individual who lives forever. So this mortality rate mu augments the time discount rate. And of course, the individual of this cohort also has a dynamic budget constraint, and that's the accumulation of assets over time, the change in assets, which is determined by the difference between income and consumption. So if that's positive, the person saves, and saving means that assets increase, so the time derivative would be positive. And income consists of wage income, W, and asset income, which is interest income, plus income due to the life insurance company. So we assume that households save in the form of annuities. So if they die, their assets are basically redistributed among those who survived. And therefore, the mortality rate mu shows up in the individual budget constraint as a redistribution from those who died to those who survived due to the life insurance company that sells annuities. And with such a setting, we get the individual Euler equation that we are now very well familiar with already, in this case for a logarithmic utility function, where consumption growth is positive if and only if the interest rate is greater than the time preference rate. So if the financial markets overcompensate me for my impatience, then I will save, and saving means again consuming less today and more in the future. So that means that consumption growth is steeper. However, this is not the end of the story in a framework where we do not have a representative agent, because we only solved the utility maximization problem for one cohort, or the member of one cohort, on the previous slide. Now, if we want to know aggregate consumption and aggregate assets, we need to integrate over all cohorts that are alive at a certain point in time. So we need to integrate from time minus infinity up to time t, which is now, of all the decisions of all the cohorts multiplied by the cohort size with respect to consumption to get aggregate consumption. And with respect to assets, we also need to integrate over all cohorts that are alive. So we take their assets and multiply also by the cohort size to get aggregate assets. And this then applies aggregate laws of motion for consumption and assets in the following way that we have below here, where the first one can be interpreted as an aggregate Euler equation if we divide it by aggregate consumption again. And what it shows is that this differs crucially from the individual Euler equation, because there is an additional term that we have here that depends on the birth rate and the death rate. And this term shows up because of generational turnover. At each moment in time, a fraction of older individuals who have had more time to accumulate assets in the past, who therefore have a higher asset level, are richer and can afford more consumption, they die and they are replaced by newborns without any assets who can only afford the lower consumption level, so that this ongoing birth and death process slows down aggregate consumption expenditure growth as compared to individual consumption expenditure growth. So the aggregate Euler equation will reflect demography and will exhibit a lower growth rate as compared to the individual Euler equation in terms of consumption growth, with the difference being determined by the demographic structure and the difference changing if we change the fertility rate and the death rate. With respect to the asset accumulation equation, not much changes because of the life insurance company that only redistributes wealth between individuals who died and those who survived. So actually the mortality rate mu integrates out when we aggregate over the different cohorts. Overall, in a nutshell, aggregate consumption growth now depends on the fertility rate and the mortality rate. And since the aggregate Euler equation is a crucial equilibrium relationship that we need later on to calculate the growth rate of the economy, changing beta and mu will have effects on economic growth. Now we turn to what changes on the production side of the economy. And here we have to distinguish again between the Roma case and the Jones case, where in the Roma model a central assumption is that the population size stays constant. That means in our case that the difference between the birth rate and the death rate has to be equal to 0. So the birth rate is equal to the death rate, and we can only analyze changes in the economy when both of these rates change at the same time in the same direction to the same extent. So if we analyze increasing life expectancy, we would have that the mortality rate decreases and the fertility rate decreases, and essentially this would cause population aging. The mean age of the population would increase. In the Jones case, by contrast, we can analyze situations where the population growth rate stays positive. So we can change the fertility rate and the mortality rate independently of each other, as long as population size is positive, population growth is positive, of course. And then what we have is that in the Jones framework, both the supply side effects and the demand side effects are present during the transition towards the long run balanced growth path. And in the long run, the economic growth rate is determined by population growth. We already know this from the chapter on the Jones model. So in the long run, only the supply side or the production side effects matter for economic growth in the Jones case, and the demand side effects die out during the transition. They matter during the transition, but not in the long run balanced growth path. In the Roma case, basically, the population size effects on the production side of the economy are switched off by the fact that the mortality rate is always equal to the fertility rate, but the demand side effects are present. So if households change their behavior, this will have effects in the economy, and these effects will have permanent growth effects due to the strong scale effect being present in the Roma case. Now, I do not solve the model here in this chapter because we already solved the Roma model and the Jones model in the corresponding chapters. The only thing that you have to do is to replace the individual Euler equation by the aggregate Euler equation that features demography, replace the asset accumulation equation by the corresponding asset accumulation equation that we have here, or the resource constraint of the economy, and plugging in the demographic assumptions in the resulting economic growth rate that you get in the corresponding model. And what you would find then is that increasing life expectancy, which means a decrease in the mortality rate mu, would lead to more saving in the Roma framework, which would put downward pressure on the interest rate because you have a higher capital stock in equilibrium, which in turn means that there are better incentives to carry out research and development because R&D projects or their revenue is discounted with the interest rate. So the discounted stream of the revenues of R&D projects, of the operating profits of intermediate goods firms, that's the incentive to carry out R&D. And if ceteris paribus the interest rate decreases, the discounted stream is higher. And that would speed up technological progress and economic growth would rise in the Roma model. In the Jones framework, we have that increasing life expectancy, so a decrease in the mortality rate mu, leads to faster population growth and thus rising technological progress and economic growth. And the opposite holds true for a decrease in fertility, so that decreases population growth and therefore decreases economic growth. Now that's a pure long-run effect that materializes on the firm side of the economy. But during the transition to the balanced growth path, we also have similar effects as in the Roma model. And that's when we, for example, make calculation on the effects of lower fertility and increasing life expectancy to the extent that population growth slows down. So where fertility decreases by more than life expectancy increases, where we would have a decrease in population growth in the long run, but as we will see in a simulation, we have an increase in economic growth in the short to medium run. Now, this experiment with a decreasing fertility rate that falls by a larger extent than mortality in the Jones model can only be made numerically. We cannot solve for this transition phase analytically. And this numerical simulation is exactly what we do in the paper with Timo Trimborn. And here you see the central result of this paper, where we simulate economic growth and assume that we are in the balanced growth path initially, where the growth rate of the economy is this dashed line here, close to 1.45%. And then at time period 0 here, we have a decrease in the fertility rate and a decrease in the mortality rate to the extent that we can observe it in different industrialized countries over the long run. And such a decrease would in the long run lead to a decrease in population growth. So in the long run, also economic growth would be lower. But during the transition in the short run and in the medium run, we have that the demand side effects that I explained in the context of the Roma model, that there is more saving, more capital accumulation, the interest rate goes down, this provides an incentive to carry out research and development and so on, increases economic growth above the level that we had in the initial balanced growth path. And this increase then leads to a growth rate that is higher than the growth rate in the previous steady state for about 20 years, and only then it becomes lower. And the economic level of GDP, per capita GDP, is higher than in the baseline case, even for almost 40 years. So if we assume that this model is the correct description of the world, what we would see in case of such a demographic change of a decrease in fertility to a larger extent than a decrease in mortality over the long run, which is what we observe in reality, then we would actually see an increase in economic growth for quite a long time, and we would see that the country that faces such demographic changes is better off in terms of the level of per capita GDP for a substantial amount of time, and only in the very long run the negative effects would dominate, basically. So overall, we can summarize that there seem to be positive growth effects of rising life expectancy on the demand side, because that induces people to save more, this decreases the interest rate, provides more incentives to carry out R&D projects, and on the supply side or on the firm side, because population growth increases the growth rate in the number of workers and therefore in the growth rate of the number of scientists, and therefore the technological progress and long-run economic growth, basically. Then a falling fertility rate has negative growth effects in the Jones case particularly, because in the Roma case we cannot analyze it. But even if the fertility rate falls, and if this occurs at the same time that the mortality rate falls, there can be positive growth effects that last for quite a long time. So this framework potentially can explain some of the empirical findings that we have regarding population aging and economic growth, where it is often found that there is a positive relationship between per capita GDP level of countries that have higher life expectancy and economic growth, and even countries that are older on average, where one would expect that their economic growth rates decrease. However, we have in the long run that a decrease in fertility would definitely decrease economic growth. And now whether this is indeed the case is empirically questionable, as we know that cross-country growth regressions tell us that countries with a higher population growth rate typically have lower economic growth rates, but you can also introduce into this model a quality-quantity trade-off effect, as we did it in the chapter on human capital in the semi-endogenous growth model, and then you would even get a positive relationship between falling fertility and economic growth. So if fertility rate falls, economic growth would increase.